Hello, everyone. Hope you're doing well. Let's go through a little bit more about how to use Stone-Weierstrass and Arzela-Ascoli beyond just the examples that we were initially given in the problem. We'll also discuss here about when you know you need to be using one theorem other than another. Typically, what's happening is you're either being asked to show that a certain set is compact or perhaps even pre-compact, like we saw in our quiz a couple of weeks ago, or you're being asked to show that a particular set is dense inside of a larger set, or perhaps that it's equal to the entire set if you happen to be able to show that it's a closed set. Whether you're being asked to do one of those things can be a tell for you about what theorem you are being asked to use to work through the problem. Like, take a look at question 1 here, which might be a bit familiar. Let S be the set of contractions from video lecture 6.1.4, also the one in video lecture 7.0 that we went through and dove into a bit more. That is, we would say a contraction with domain 0, 1 is inside of the set S if, when you evaluate it at x equals 0, the y value you get out of it is 0. Show that S is compact inside of the set of continuous functions from 0 to 1. Now, I put in a little bit of a note here, just kind of parenthetical on the bottom here, that what I mean here are the continuous functions with domain 0, 1 and with range in the real numbers. Although that's okay, we have a collection of functions that have a range inside of -1 to 1, but their codomain can be a bit larger. They can be all of the real numbers. This also helps standardize the notation that sometimes I will use versus the book. If I do not put a range in this little parentheses by this capital C, then I mean this first set, 0 to 1, to be the domain, and the codomain is understood to be the real numbers. So what's going to tell me that I need to be using Arzela-Ascoli here? I'm asked to show that a set is compact, and we recall that, looking at Arzela-Ascoli right down here, that if you have something that is already a compact metric space, then a subset K of the continuous functions on that compact space is compact itself, if and only if it is closed, bounded, and equicontinuous. So we want to show compactness of a collection of functions. And in order to do so, we want to use Arzela-Ascoli. Stone-Weierstrass doesn't make sense here, because what it tells us is that we have a density of this set inside of the larger set of functions, and that's not something that we're trying to show here. So let's go through and see if we can use this theorem to prove this question without having to come up with a diagonalization argument. We only need to show closed, bounded, and equicontinuous. Let's see if we can do those three things. So let's start with figuring out how to show that this set is bounded. Bounded, remember, means that the largest possible distance between any two functions inside of the set is completely bounded. But that's something that we've already shown. We've already shown in bounded that that is possible. Remember that we say that's the distance that we are using is the infinity metric, which is the d sub infinity of f comma g is the supremum over all possible x values of the absolute value distance between any two any y values at that corresponding x value. And you may remember us from either the video lecture 7-0 or from the previous video lecture in our drawings that the largest possible swath that any function inside of here can take is inside of these lines of slope 1 and -1 respectively, starting here at where all of these functions share a common point at f of 0, 0. That is the highest possible point it can go at is 1, 1, and the other one is 1, -1. Just as a quick reminder as why that is, remember that contractions have derivatives bounded by 1 and -1. So what's the highest possible way that this could go up? Is if the derivative was exactly 1 the whole way through. Think if your derivative ends up being 0 for a little bit, and you think, oh, I've got to catch back up. You can only go at a slope of at most 1. You cannot catch back up all the way to the other point, because that would mean that you have to heighten the slope beyond a slope of 1 to be able to get to that point. Same thing for going all the way down here. The lowest possible way that you could descend as a function is if you're going at a slope of -1, going from left to right. So what does that mean about any two functions inside of the set S? If f and g are in S, then we know that f of 1 is equal to In fact, this is the fundamental theorem of calculus here. F of 1 minus f of 0 is equal to the integral from 0 to 1 of the derivative of that function in between those two values. That is, f of 1 is equal to 0 plus the integral from 0 to 1 of f prime of x dx by adding over f of 0 and also subbing in what we know f of 0 to be. And we also know that whatever we're integrating inside of here is something bounded above or below by 1. So what does this mean? F of 1 is going to be the absolute value of f of 1 is going to be equal to the absolute value of this integral for dx. And that absolute value, whatever it is, since f prime of x is less than or equal to 1 in absolute value, then this has to be equal to less than or equal to 1 times the distance between the 2 points that are bounds of this integral, which is 1 minus 0. So the farthest possible place that you could have any two functions be, one maybe could be f of 1 could be 1, and the other f of 1 could be negative 1. So the largest possible distance, primum, over all points inside of this, f of x minus g of x here, is going to be, by a similar argument, we could go through and set up what these integrals are and say that this is going to be equal to the supremum over all x inside of 0 to 1 of the absolute value of the integral going from 0 to x instead of to 1, just to kind of specify that this supremum needs to be taking place at any of these values here, of the difference between f prime of x minus g prime of x dx. And so you can imagine that the worst possible scenario for what this integral could be is f prime of x is 1 and g prime of x is negative 1 all the time. Like you're just looking at these two lines right up here. In which case, what you would have is you'd be integrating 2. So this is the supremum over all x in 0, 1 of 2 times x minus 0, where x is somewhere in between 0 and 1. So the supremum that can be taken in is when you would plug in x equals 1. And the largest possible distance between any 2 points here is 2. This is less than infinity. So the set S is bounded. So that's what it means to show that a set is bounded. It's to say that any two functions inside of that set are in fact bounded away from each other. And note that the fundamental theorem of calculus ends up being useful here because it tells us that we can write differences between two function values by looking at integrals of their derivatives. And the thing about contractions is we know a lot about these derivatives and how these things look. So we've shown that this set is bounded. Let's see if we can go through and show that it is closed. In order to show it is closed, we would need to say that something that is a boundary point of this set. And if you take a sequence of functions that are inside the set, then the function that they limit to is also in the set. We want to show if f sub n is a subset of S and f sub n converges to f, which is going to be itself just some element inside the continuous functions, we want to show that f is actually an element of S. That is, f is not only just a continuous function, it is a contraction. And it starts at the exact same point of x equals 0. So that's what we would like to show here. Well, we know that f sub n converging to f in the continuous functions from 0 to 1 by one of our theorems that we've discussed is that this level of convergence is actually uniform convergence. So we can write the double arrow here to say that the functions f sub n converge uniformly to the function f. Note that says a few things. F sub n is continuous, implies that f is also continuous. All right, pretty good, pretty good. We could even say a little bit more. We've shown that if f sub n is continuous, then f is continuous. In fact, we know that f sub n prime, which is, recall, the limit as x goes to a of f sub n of x minus f sub n of a divided by x minus a, that this limit exists and is bounded, then that's actually going to end up implying something else. That is that f prime, which is the limit as n goes to infinity of these limits here for f sub n of x minus f sub n of a over x minus a, is actually going to end up existing. Now, to be clear here, this passing of limits to make this happen, what I'm about to do here to show this, is something that isn't necessarily true for any function that you might put here or any kind of situation that you might find yourself in. Notice that what I've done to get from one side of this limit to the other limit on the right-hand side is that I flipped what two things I'm taking the limits of. And being able to do that is actually kind of takes a little bit of work. But it turns out that as long as we have functions that are converging uniformly and the values at which they could be converging are bounded, then we end up being okay. Sometimes that is discussed in an undergraduate analysis class, and we'll just kind of have to take it on faith for this particular place. By the way, if you find that useful in some other sort of context, feel free to use it as you would. That is, that if you have functions that are converging uniformly and all of your values here for what these functions can be, these derivatives are bounded, which they are, they're bounded by 1, since these are contractions, then we can pass these limits right past each other. So why did I do that? Because now that the limit as n goes to infinity for this function, I just have to find what this limit of fractions is, but it's the same sort of thing as what we would typically have. Limit as x goes to a of taking the limits of these f sub n's gives us f of x minus f of a over x minus a. So this exists and is bounded by 1, which is exactly what it means to be inside of this set. Finally, we have f sub n equals 0 for all n, which implies that f of 0 equals 0 by convergence of the sequence f sub n. So all of these things put together give us that, in fact, this function f that we have is indeed an element of the set S. It is continuous. It is differentiable. Its derivative is bounded from -1 to 1. I need to be putting absolute values around in here just to be able to say that these don't all have to be positive. It's bounded by 1 right there. And so there we go. That should help us finish this thing out. And then the last thing is the most important thing for us, which is showing equicontinuity. So equicontinuous. Let's remind ourselves of what this definition is, as this is our new one for us. For all f and s, and for all epsilon greater than 0, so let's see. So actually, I need to be saying this in a slightly different order. For all x inside of 0, 1, and for all epsilon greater than 0, that there exists a delta greater than 0, such that for all f inside of our set S, x minus x naught, the distance between these two values, which would be an absolute value, but we'll go ahead and write it in our metric space notation, that the distance from x to x naught inside of this space is less than delta, implies that the distance between corresponding y values for these functions is less than epsilon. Recall that the main difference here for equicontinuity is that you're having to be able to choose an epsilon delta pair that works regardless of the function that you're working on inside of the set S. But that's actually not going to be that big of a deal for us, because what's neat about this is that the set we're working on has a given ratio between how much its x values can grow versus how much its y values could grow. That sounds a lot like a slope to me. And we know that the derivatives of these functions are bounded by 1 and -1, respectively, looking at upper and lower bounds. So we should be able to get this equicontinuity. In fact, we should be able to get kind of what we might call a uniform equicontinuity, because we're going to be able to make this choice without having to worry too much about what this x value is. So let's fix epsilon greater than 0. And we're going to be able to choose delta is equal to epsilon. Now, let me go through and show you why I'm able to make that step by going through and first working through the other part here down underneath, what we're going to be showing as part of our proof. Then x minus x naught is less than delta implies that we want the absolute value of f of x minus f of x naught to be a specific value for being inside of this space here. So let's see how we can make that work. Well, we know that we can rewrite this as the f of x minus f of x naught divided by x minus x naught times x naught, something like this. So notice what I've done is I've multiplied both top and bottom by this value of the absolute value of x minus x naught. And what good does that do to me? What that does is it makes this thing on the left look a lot like a derivative, doesn't it? It's not quite a derivative, but we can get the derivative involved by replacing this thing on the upper part, this integral of the f of x minus f of x naught, using the fundamental theorem of calculus once again, that this is the derivative of this f prime of t dt of value going from x naught to x, and dividing that by x minus x naught times x minus x naught. You might remember this as being the average value of a function f prime over a given interval going from x naught to x, especially if you kind of have to do this. I've seen this before in AP calculus classes, where this becomes the average value of the function. So this is the average value of f prime on the interval going from x naught to x. And guess what? That average value of f prime is going to be less than or equal to 1, because the whole of f prime is going to be less than or equal to 1. So this is going to be less than or equal to x minus x naught, and we want this to be less than epsilon. So why not go ahead and just make our choice for delta to be equal to epsilon? So that gives us what that choice should be, and in fact, that ends our proof for showing this uniform version of equicontinuity. See if I can get one lasso around all of it. That's the best we can do. So let's bring that back up. There we go. And then there you go. That is our argument for equicontinuity here. It's a neat little thing here to be able to see that basically we are able to break down the same argument that we did from before into 3 separate arguments, 2 of which we are a little bit more used to, although maybe we have to practice doing these for functions since we've done them a lot for individual numbers inside of sets like we did back in weeks 3, 4, and 5. And now that we're getting used to seeing these with functions a little bit more, maybe that's going to be a bit of practice for us. But overall, this becomes a much quicker way typically of showing how to go through and set up a compactness of a set if you're able to break it down into these 3 components. We'll get some practice with this in our homework. And then we have this question that asks us to show that the space of polynomials, which is given right here as the set P, is dense inside the space of continuous functions on the closed interval going from 0 to 1. Important before we can use either of these theorems is that the domain needs to be a compact set. We need to be looking at a set that is closed and bounded in the real numbers, or that is somehow totally bounded and closed in a metric space, or using the definitions of compact that we have looked at previously. So how are we going to proceed with this one? Notice the difference in how this question is phrased. In the previous one, we were looking at compactness, which tells us that essentially we can be working with elements inside of that space using an analyst version of finiteness. It's the closest that we could get to something that is neat and packaged nicely together like a finite set would be. We know that from our reading, that's kind of like the open covering versus it gives you a finite subcovering way of thinking of compactness. And that is something that's very useful for us in the notion of everything is very close to a certain number of points, spatially speaking. So now taking a look at question 2, we have a space which we want to show is dense, which we know means that this particular set kind of weaves its way through the entire set. When it doesn't have to be a small or finite set, it weaves its way through, so that anytime you're considering an open ball inside of that set, then you know for a fact you're going to be able to find a polynomial in there, which is something wild to think about for the space of functions. That's what this is saying, is that you can take a function, even something just like e to the x, on the set going from 0 to 1, and you can find a polynomial that approximates it very closely. What this means is this. Another way that this question could have been rewritten is this. Let f be a continuous function on 0 to 1. Then show there exist polynomials P sub n, which are also going to be defined on 0 to 1, such that the polynomials P sub n uniformly converge to your function f. Not only do they just get there kind of eventually, they actually uniformly converge. You can imagine this as like you're taking something like e to the x, not a polynomial at all, but that you can take polynomials that eventually form fit to give you the type of function that you're getting. You can perhaps maybe start everything to have the same point at x equals 0, and then start trying to form fit the rest of them by changing their derivatives in a specific way, by looking at what the derivatives of the polynomials you want to be, and so on and so forth. And we could do that. We could go through and make a whole case as to why you don't even need Stone-Weierstrass theorem to do this. That's the whole idea behind Berenstein polynomials in our reading from section 4.8. But Stone-Weierstrass makes this a lot faster. What it says is this, that we can take a function or any set, as long as it is closed, as long as it is an algebra, as long as it contains the unit function, right? And I think if I'm going through all of them, it needs to be closed, needs to be an algebra, needs to have unit in it, and it needs to separate points. That is, there need to be, anytime that you have two separate points, like inside of the closed interval from 0 to 1, like 1/4 and 3/4, then there need to be two functions that have separate y values or on that function, or there needs to be a function that gives those two x values separate y values. Then once you have all of those properties put together, then what you get is a space of polynomials, which is dense in this set, which is going to be pretty neat. So we'll walk through those steps one by one. Let's see if we can show that the space P separates points first. So what does it mean to separate points? Separating points means that if you have x is not equal to y inside of 0 to 1, then that implies that there exists a function f inside of our set, which is today P, such that f of x is not equal to f of y. Notice that this is not necessarily saying that the function f is injective, because it's just saying for any 2 points that you have, x and y, you can go out and find a function f that has those two different y values. However, if you are able to find an injective function for f, then that automatically shows that the polynomial separates points. Why is that? Because you now know that this implication follows immediately regardless of the points x and y and how these things work. So for all x not equal to y inside of this set, we want to show that there exists this function f such that f of x is not equal to f of y. Formally speaking, that's how we can think through this. So how are we going to do this? Well, the good news is we actually have an injective function amongst the polynomials. Let f of x equal x. Then f is in P, because it is a polynomial of degree 1. And if we have two values, x not equal to y, then that will imply that f of x, which is x, is not equal to y, which is f of y. And that gives us the separation of points that we need. Something nice and easy for the fact that we just work with polynomials here is that we get to work with a lot of injective functions when we do that. Pretty neat thing there. So that tells us that this space separates points. What else do we need to show? We need to show that I wanted the colors to be different. There we go. So the next thing we want to show is that the space of polynomials, we don't have to necessarily show that it's closed, even though I mentioned that before. Showing that the space of polynomials is closed would mean that the space of polynomials is the entire set of the continuous functions from 0 to 1. In fact, the space of polynomials is not closed. You can find a limit of polynomials that approaches e to the x, or something like this, something that is definitely not a polynomial. So it's not a closed set. But let's talk about what else we need to be showing here. Does P vanish anywhere? If it vanishes nowhere, then we're good to go. Another way to show this is, first, to recall the definition of vanishes nowhere. There does not exist, or for all x inside of our domain, in this case 0 to 1, that there exists a function f inside of the polynomials such that f of x is not equal to 0. So for all x inside of 0, 1, we're basically saying that there is going to be some function here where f of x just doesn't equal the 0 function. Otherwise, you have this other kind of way of looking at the Stone-Weierstrass theorem that we talked about a bit in our previous, or in 7-1 video lectures, which is that you have kind of this set that is dense inside of a subset of the continuous functions that you're looking at. But this set actually vanishes nowhere. For all x inside of 0, 1, there does exist a function f in P such that f of x is not equal to 0. And even though that function can change regardless, given the choice of x that you're given, we actually have a function that is 0 nowhere. Let f of x equal 1. Then f is in p. This is a degree 0 polynomial and is very much in the definition of polynomials that we had to begin with. This is where a sub 1 through a sub n are all set to be 0 as constants, and a sub 0 is equal to 1. Then we have f is in p, also f of x equals 1, which is not equal to 0 for all x inside of 0, 1. And that shows us that p indeed vanishes nowhere. So that gets us where we would like to be for this point. One of the most important things, and maybe the newest thing for us, is that we also finally want to show that P is an algebra. We recall that something is an algebra if whenever you have two functions inside of that space, then that means that their product is also inside of that space. If f comma g, these two functions are inside of the set P, then in fact their product is inside of the set P. Well, how would we show that? Let's take two polynomials, a0, a1x plus dot, 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 plus an x to the n, and let's multiply it times another polynomial here. I'll use different lettering for this one, b0 and b1 rather than a0 and a1. And I'm also going to give it a different index because I don't know if the degrees of these two polynomials are the same. And if I use the power n in this first polynomial, just like I did in the second, then I would definitely be assuming that they had the same degree, that degree being n at that point. So I'll use m instead to get this. And so what I want to do is describe what this product looks like, and then hopefully describe it in a way that's good enough that shows that this is actually a polynomial. So how am I going to go through and do this? Well, I know that this is going to be the product of going through and kind of using the FOIL technique on each of these things. Some of you may have some success here using induction to make this a bit more clean than maybe what I will try to do. And is induction on the degree of each of these. But we could also just consider this as distributing one set of parentheses to each of the terms inside of the other parentheses. And if we then distribute back into what that is, then what we're going to get is the product of as I goes from 1 to n, as well as the product as j goes from 1 to m, of all functions of the form a sub I, b sub j, x to the I plus j. So this formula here is the formula for what this product might look like. Let's talk a bit about some of the symbols that we maybe have not seen before. This capital pi right here does not mean anything trigonometric or circular in any way. It means take the product instead of the sum, like a series, as the index I goes from 1 to n. We know that the capital sigma is there for whenever we want to be summing something for an index like this. And I'm using that exact same type of notation for a product and using capital pi to denote that. Here, my index for I is going to be the subscript of a sub I. You can see a0, a1 through an. And now that I'm highlighting that, I realize that I and j actually start at 0 rather than at 1. So allow me to change that. So that these indices start at I equals 0, and then they continue to multiply all the way up to a sub n times any of the terms inside of here, which themselves are also a product, as j goes from 0 to m of those b sub j and those constants. Now, when I am multiplying together those constants, I'm also multiplying together factors of x. In the a sub I, I'd be factoring together x. This is a sub I times x to the I. And in b sub j, I'd be multiplying that times x to the j. And when I multiply those two things together, I add together their powers, and that gives me this formula for what this product might look like. Now, what this looks like doesn't quite look like a polynomial yet, but I'm going to write something here and see if you can get behind what I'm about to write. This is going to be equal to the sum as, what we say k goes from 0 to n plus m, of the sum as I plus j is equal to k, of a sub I, b sub j times x to the k. So let's talk a little bit about what this series looks like. First, I have written the product in terms of a series, or so I claim, and let me talk a bit about what's going on. This series inside of here is saying that I would like for the indices in I and j to multiply or add together to give me the power of k that I'm working on in this. So, for example, if k is equal to 2, then this sum is going to pick all possible pairings of I and j that give me 2 for the for the value of k, so that when they add together. So, for example, this is going to be the sum a sub 2 b sub 0 plus a sub 1 b sub 1 plus a sub 0 b sub 2. Think of it as like combining together all of the like terms, all of the constants that have x squared in them. They're all getting combined in this series. Now that's just for the kth term, but the sum on the outside says the powers that I want to consider for that x to the k are going to start at 0 and then go all the way up to n plus m. This now looks a little bit more like a polynomial. In fact, I could write it out a little bit more if that would be useful, but I think that we're kind of good enough here. Each of these is a constant times x to the k, and then we are adding over x to the k powers. So that looks a little bit more like the kind of polynomial that we're used to seeing. So this is in the space of polynomials. This was an arbitrary polynomial. This was an arbitrary polynomial, and therefore their product, being another polynomial, shows that this space is indeed an algebra. So let's just check and make sure, got the theorem right here, that I've gotten everything that we need to be covering. We need to be able to say that this is a compact space, that this is a subalgebra of the continuous functions that separates points and that vanishes nowhere. And then that should work. That is what we need to do to be able to claim by Stone-Weierstrass. That implies that this P is dense inside of C going from 0 to 1. I wanted to give these examples because this is really what we're going to be focusing on in this class, in our homework and so on and so forth, is I want us to be focusing on more on how these things are used rather than how they're proven. Now, for many of you, if you're going to go on and do some things with proofs, either for your final project or for some sort of later project that you have outside of this program, you probably do want to be reading through these proofs one more time now that you see how these things are used and think, okay, why was that useful? Why did I need to show this algebra thing? What is very helpful about that? And you'll learn a little bit more about the lattice that is used inside of this proof and start trying to think a little bit about, okay, well, how can I delve into this subject a little bit more? You are free to ask me any questions about the proofs because you're reading through it. Don't think that just because I'm not going to be talking about it in class very much doesn't mean that I don't want you to feel like you get the chance to really look through it and learn a lot from it, because I think that that is important. I want you to start looking through these proofs and also the way that they are worked and feel like you've got the amount of handle that you would like with either of those two things. We'll be focusing on this more practical way of utilizing these theorems, but we've worked so hard to be able to understand these proofs to some extent that I want you to feel like you can start really diving into what these arguments are, especially since we've talked about compactness. We've talked about all the different ways to formulate it. We've talked about equicontinuity and how the diagonalization argument can be used to show compactness of spaces of continuous functions. And so why not go ahead and give it a crack? Take a look around, see what you can find out as far as the proofs here. But feel free to use these as references for how to go through and utilize these sorts of arguments to show Arzela-Ascoli or Stone-Weierstrass in these kinds of contexts. That'll do it for me today. Thank you so much. Have a wonderful day.